We live in a world surrounded by sensors. They monitor air quality, track our heartbeat, and help our cities run smarter and safer. But as our technology becomes smaller, faster, and more flexible, the rigid materials struggle to interface seamlessly with soft and biological systems like human skin. So, how do we bridge the gap between high performance and mechanical flexibility? Enter graphene. It's not just a wonder material. It represents a fundamental shift in how we detect the world at atomic scale. It has only one layer of carbon atoms, arranged like a honeycomb, what you often hear is stronger than steel or conductive like copper. For a sensor engineer, one of the most critical factors is the extremely high surface-to-volume ratio. Every single atom is exposed. Nothing is hidden beneath the surface. That means even tiny disturbances like a single molecule landing can noticeably change the electrical signal. It fills the world atom by atom. Now, graphene isn't the only player. It launched an entire family of wonderful materials like MOS2 or Maxine. Each has its own unique superpowers, but graphene remains the star for sensing because of its ultra-high carrier mobility. Electrons move through graphene very easily, facing almost no scattering. This leads to an extremely high sensitivity, meaning we can detect events that many materials might miss. Turning graphene into a sensor is simple, at least in principle. Scientists place a tiny strip of graphene between two electrodes and pass a small current through it. The specific structure forms either a graphene resistor center or with a gate, a graphene transistor. When something touches or interacts with the graphene, there will be a measurable shift in resistance or conductance. This high sensitivity unlocks an amazing range of applications. In environmental sensing, graphene can detect pollutants like nitrogen dioxide or ammonia at concentrations even down to parts per billion, or in some cases, parts per trillion. In healthcare, flexible graphene patches measure glucose, sodium, and lactate in sweat without needles or painful pricks. In robotics, via piezoresistivity, sensor networks can act as electronic skin, giving robot tactile feedback sensitive enough to feel the weight of a feather. Together, they're helping us build sensors that are thinner, faster, and more flexible. Graphene isn't perfect, at least not yet. The next big challenge is scale. How to make large, uniform sheets that perform consistently in factories. Another challenge is that pristine graphene is so sensitive. It often reacts to everything. To fix this, we use surface functionalization. We coat the graphene with specific linkers like aptamers or antibodies that grab only the target molecule, ignoring the rest. Graphene was just the beginning. Its discovery opened the door to a new world of two-dimensional materials, each with unique superpowers that could transform how we sense light, pressure, chemicals, and light face off. I'd love to hear your thoughts, and don't forget to write it down in the comment section below. Meanwhile, if you'd like to follow me, my LinkedIn URL is mentioned on the show notes below.